Hello, and thank you for joining us. In today's presentation, we will be discussing liquid sample introduction techniques. Our presenter is Fred Smith, Technical Product Manager for Teledyne CETAC. We will be taking questions, so please feel free to submit them throughout the presentation using the question function, and Fred will respond individually via email shortly after the webinar has concluded. This webinar is being recorded and will be available for viewing within a few days. Now I'm going to turn it over to our presenter, Fred Smith.
Thank you for the introduction, Shelley, and thank you everyone for attending today. Today's webinar is going to discuss a very timely topic, and that's the measurement of nutrient and trace level elements in juices and food products. And we are going to explore using an enhanced nebulizer accessory that is ultrasonic nebulization, and use ICP-OES optical emission spectroscopy for the detection of trace and minor elements. So consumers are more concerned about the levels of potential toxic elements such as arsenic, cadmium, lead in beverages and food products. And of heightened concern are food products intended for consumption by infants and children. So reliable and precise methods of food analysis are important to maintain the safety of the food supply. In addition, accurate data is needed to comply with food labeling requirements for nutrients, which are present at higher levels, such as calcium, iron, potassium, and sodium. So the accessory we're going to talk about today is an ultrasonic nebulizer, and it's an accessory for ICP optical emission spectroscopy that enables higher sample transport efficiency versus a standard pneumatic or gas-based nebulizer to the plasma. This can be helpful for detection of more difficult elements such as arsenic, lead, antimony, selenium, and thallium while using ICP-OES detection. So this webinar will describe the use of the ultrasonic nebulizer, and we'll look at what improvements we can make in the detection of trace elements in juices and a variety of food matrices. So principle of operation of the ultrasonic nebulizer: in place of a regulated gas flow for generation of a liquid sample aerosol by pneumatic nebulization, the sample liquid is pumped across a quartz plate with an underlying oscillating piezoelectric crystal. So the point is, we're not going to use a gas flow to shear the liquid into a usable spray. We're simply going to use that gas flow to carry the aerosol that's generated by a different process, in this case, the oscillating crystal or the piezoelectric. Those oscillations then will break up the liquid flow and cause the formation of a sample aerosol. This type of nebulization is typically up to about 10 times more efficient versus a conventional gas-based or pneumatic nebulizer for conversion of the liquid sample into a usable aerosol. So first, a front view picture of the system that we're going to discuss today, and it's termed the Teledyne CETAC U5000 AT+, and I'll explain a little bit about the name in some of the coming slides. But there you can see the overall dimensions of the unit, the width, depth, and height, and it very much is a benchtop device or a device that can be easily placed on a laboratory cart. So you can leave this permanently in front of your ICP, or you can install it and use it as needed. As we'll get into some of the details, it's very straightforward to install. I do want to point out on the front of the unit, in the lower right, are two temperature controllers. These are set at the factory, and these controllers operate to control the temperatures of the desolvation system that's used in the ultrasonic nebulizer. Because it's a more efficient nebulizer and we're generating more liquid aerosol, we do need to remove that excess water to keep the ICP plasma stable. So a schematic of the system. There you see some of the details of the desolvation system. So And the lower left is the transducer, which contains the oscillating piezoelectric crystal. And we're going to pump sample across that faceplate. And as that vibrates or oscillates, the aerosol will be generated. The argon gas flow, where it says AR in, comes in at the top of the spray chamber, and that's simply used to carry the aerosol through the system and to the host ICP. Any excess liquid goes down to drain and to waste. But in the desolvation system, we have what's called a heated U-tube or J-tube to keep the sample aerosol in a vapor form. Then when it goes into the condenser, we remove the excess sample solvent, and that drains out to waste. So what then passes to the ICP is a aerosol of dried salt particles with most of the water vapor removed. And of course, that's to stabilize the ICP. So again, a couple of important features of the U5000 AT+. It has an integrated desolvation system, and it's an electrothermal system or Peltier cooling. That removes excess sample aerosol solvent for plasma stability. It also has a built-in drain peristaltic pump. This removes the condensed sample solvent, so there's no need to use the host ICP-OES peristaltic pump. That peristaltic pump can be reserved for pumping sample and any reagents or internal standards into the sample system. So a close-up of the transducer, this is the part that takes the place of the pneumatic or gas-placed nebulizer. The piezoelectric crystal is a small disc-shaped device, and you see it pointed out by the green arrow, and it's sandwiched with a quartz faceplate, and that's called out with the red arrow. Okay. On the back of the unit are electrical connection to generate the piezoelectric oscillations, and the rest of the construction is a heat sink to remove any excess heat as the crystal vibrates. So the instrumentation that we're going to use today, the ICP-OES system that we did the test with is the PerkinElmer Avio 500. The ultrasonic nebulizer, again, is the CETAC U5000 AT+ model. And for sample preparation, we used a CEM Mars 6 microwave digestion system. So, installation steps. I do want to go over these with a little bit of detail, but just to show you that the installation steps are very straightforward. So first we remove the standard nebulizer and spray chamber from the host ICP. We would connect the nebulizer gas inlet tubing line from the host ICP to the ultrasonic nebulizer, and then a sample out tube from the U5000 AT+ to the ICP torch. Connect a power cord and turn on the power, and allow the heater and cooler to stabilize. That will take about 10 minutes. Then simply start the ICP. Introduce your tune solution, press one button, the operate button on the front of the unit, to begin nebulizing tune solution and then samples. And adjust gas flows for best signal, primarily the nebulizer gas flow from the host ICP. Overall setup only takes about 15 minutes. You use the host ICP-OES peristaltic pump to introduce the samples to the ultrasonic nebulizer, so there's no need to acquire a separate standalone peristaltic pump. There's no computer control required, and there's no software installation needed. One button operation. After it's powered up and at temperature, as I'll show you, you simply press one button and the aerosol will be generated. Sample introduction to the ultrasonic nebulizer can be automated by connecting the sample inlet line to an appropriate autosampler, such as a CETAC ASX series, such as a 280 or a 560. Now, I didn't mention the tubing lines to interface the ultrasonic nebulizer to the host ICP, and this is an example of a typical interface kit. And there you see a variety of tubing. And in the lower left, there is a small connection piece. And we'll see that in more detail. That's a so-called torch adapter that allows us to adapt the sample outline to the host ICP. So I do want to go over this in a little bit of detail, just to show you the main points of connection between the host ICP and the ultrasonic nebulizer. So we'll start down in the lower left with the red call out for the power cable. That's very straightforward. You simply connect that and turn on the power switch just above the power cable entrance. Then as we move counterclockwise, in green, call out is an auto sampler, in this case the CETAC ASX280. There's the host ICP peristaltic pump, called out in yellow. We're going to use that to bring the sample solutions to the ultrasonic nebulizer. And then in orange, the nebulizer gas line. We're going to use the ICP as the source of the nebulizer gas, in this case acting really as a true carrier gas to sweep the aerosol we generate through the USN, dry it out, and send the dried salt particles to the plasma. In medium colored blue, you see the sample outline. That's simply a piece of PVC tubing that goes to the ICP torch. And finally, in bright blue in the middle, the drain peri-pump. That is built into the ultrasonic nebulizer, so there is no need to acquire a separate peristaltic pump to pump out the excess liquid from the system. So here's a close-up showing the nebulizer gas supply and the sample outline attachment to the ICP torch. So I'm going to use the nebulizer gas port that would normally supply argon gas to the standard nebulizer. Instead, I'm going to route that to the ultrasonic. And then the sample out from the USN after I've removed the excess sample solvent carrying the dry salt particles, I'm simply going to use that same torch adapter I showed in the earlier picture, a 12-5 glass socket adapter. I'll simply attach that to the base of the torch, and my connection is done. And there is a full view of what a typical setup might look like. And there we have the ultrasonic nebulizer, in this case on a laboratory cart, next to a PerkinElmer Avio 500 ICP, and there you see a ASX series, in this case a 280 auto sampler, used to automate sample introduction to the USN. I will point out in this picture, you might notice the bright yellow light down in the lower corner of the picture. That is the operate button, and that is the so-called one-button operation, and that is what I press to generate the sample aerosol. So I do have a very short little video here that I'll start, and let me go ahead and we'll press the operate button, and then we'll zoom in, and you can see the generation of the sample aerosol in the spray chamber. And then a still picture showing a close-up of that. There you see the very thick aerosol, the very thick so-called fog of sample aerosol being generated. Again, I've called out the transducer. There you see it mounted in the system, and the sample inlet line or tubing that you would connect your peristaltic pump to send the sample through and to the transducer. Again, the spray chamber is kind of a conical shaped type of chamber, and you might notice the tube coming up at the upper left of the chamber. That is the entrance for the nebulizer gas supply from the host ICP. But in this case, it's acting as a true carrier gas. That gas is not generating the sample aerosol. The transducer is doing that task. So I know this table is a little bit busy. I did want to show the operating conditions between the standard nebulizer and the ultrasonic nebulizer in these tests. And I pointed out in the color orange the two things, and the only two things that were changed. The nebulizer gas flow with the standard nebulizer is set at 0.7. When we set up the USN and did the tuning, it came down a little bit to 0.62, but that's very easy to do via the host ICP software. All the other gas flows in this test remain the same. The only other thing that was changed was the cassette, or the so-called torch position. We pulled it down slightly for use with the USN, and that we did when we removed the standard nebulizer and spray chamber. But overall, the change to the operating conditions is very minimal. Really, the main thing that's typically changed is the nebulizer gas flow. That can be adjusted, and it's adjusted in a typical range of, say, 0.5 to 0.7 liter per minute. So, starting then with the tests, the ICP-OES was calibrated using digested standards prepared in 10% nitric acid and 4% hydrogen peroxide. And this, of course, gives indication of the materials that we were using for digesting the beverages and the food matrix products. We measured 1 blank and 3 standards, and the correlation coefficient for the calibration curves to be used or valid must be better than 0.998. We used an online mixing tea before the nebulizer input for an online edition of an internal standard. And in this series of tests, we used the element yttrium, and we teed in at a concentration of 100 ppb or 100 micrograms per liter. Now, I do want to note the use of the hydrogen peroxide. That, of course, aids in the digestion of the organic materials. It also oxidizes one of the primary elements we want to look at, and that's arsenic. And it oxidizes all of the arsenic from arsenic 3 to arsenic 5. This helps improve transport of the arsenic through the ultrasonic nebulizer, and of course then gives us improved arsenic recoveries. So that's an important point. Our calibration ranges and wavelengths. Here you see the wavelengths that were used. I will point out for a couple of the elements, calcium and sodium, 2 different wavelengths were used, and that was to extend the dynamic range depending upon the concentration of these nutrient elements in the samples. So for calcium there you see the 317 and 315 nanometer wavelengths, and for sodium the 589 wavelength, which is more sensitive, the sodium 330 nanometer wavelength, commonly used for higher levels. And then the additional calibration ranges and wavelengths. Again, the other element that we looked at where we used 2 different wavelengths was phosphorus. So, sample types. There's quite a variety that were looked at in these tests. So for beverages, 100% cranberry juice, apple juice from a juice box, one of the small cardboard juice boxes that are readily available, 100% fruit punch, which is a mixture of different fruit juices, also from a juice box, dry cereal, baby food, or what we'll call wet baby food from a pouch, a donut, a common pastry. And then we wanted to look at the recoveries of some of the trace elements in some standard reference materials. And these are all from NIST, rice flour, bovine liver, and non-fat milk powder. Sample weights and volumes that were used then for digestion with the MARS 6 system from CEM. For the dry materials, such as the NIST standards and the dry foods, such as the breakfast cereal, we're using approximately 0.5 gram of material. The wet food, the baby foods, 1 gram, and the various juices, 5 mLs. And then sample preparation. To each digestion vessel, we added 8 mils of concentrated nitric acid and 1 mil of 30% hydrogen peroxide. The samples were allowed to react for at least 10 minutes in their vessels in a ventilation hood. That's to sort of get the initial outgassing done. And then caps were placed on the digestion vessels and then put in the Mars 6 system. And here was the microwave digestion program used for all the digestions. So 1200 watt power, ramp for 25 minutes, hold for 15 at 200 degrees C. After digestions were complete, the samples were cooled to room temperature and diluted to a final volume of 25 mils with deionized water. So one of the first things we wanted to look at were detection limits. Just how low could we go in detection, particularly for some of the harder to detect elements. 10 reagent blanks were measured using the standard nebulizer kit, that is the glass concentric nebulizer, and the ultrasonic nebulizer. These blanks are 10% nitric acid and 4% hydrogen peroxide after the dilution. And the instrument detection limits, or the IDLs, are calculated as 3 times the standard deviation of the blank concentration. So some detection limits for selected elements, in particular ones for toxicity and also for difficulty in detection: arsenic, cadmium, lead, and selenium. First on the left, we see the standard nebulizer IDLs. And again, these in general are maybe range from a half a ppb up into the single-digit ppb levels. But with the ultrasonic nebulizer, we can readily push these down, particularly some of the important elements like arsenic and lead below 1 part per billion. And there you see on the far right the improvement factors. So particularly important for more difficult elements like arsenic and lead. Sample spikes. So samples were spiked at concentrations and at 2 concentrations, 10 and 50 microgram per liter for trace elements, and 0.5 milligram per liter, or ppm, for calcium, sodium, magnesium, and iron before digestion. Per the US FDA EAM Elemental Analysis Manual 4.4, the percent spike recovery must be between 80 and 120% to be valid. If the analyte concentration was greater than 30% of the spike, then those values are not reported. So let's take a look at some of our recoveries. And this is the really low level spike. This is the 10 part per billion in cranberry juice and apple juice. The only one that did not come in was selenium. And that could be because of the quite low level of selenium in the sample, and of course the matrix that's there. When we did move that up to 50 part per billion, there you see in both the apple juice and the fruit punch, then the selenium did recover. So a little bit more details on some of the benefit that we can get from the ultrasonic nebulizer. We did look at the emission spectra, and this was the 10 microgram per liter, or 10 part per billion arsenic spike in 100% cranberry juice. And there you see with the standard nebulizer, we cannot see any distinct peak, emission peak from the arsenic. But with the ultrasonic nebulizer, we can. Similarly, with lead, spiked at the same level, 10 part per billion, in the same matrix of cranberry juice, we can see a lead peak with the ultrasonic nebulizer, noted by the green line. At the blue line with the standard nebulizer, we cannot really see a distinct peak for that lowest level spike. So then moving on to a more complex matrix, the baby foods. These were wet foods from a pouch. And type 1, there were 2 types of baby foods that were looked at in the study: a blend of apples, carrots, blueberries, and yogurt. And type 2, a blend of bananas, blueberries, and oats. And here you see for the 50 microgram per liter spike for the two types of baby foods, the results are really quite good. Only one in particular, and that's the selenium in baby food type 1 was low, and that perhaps is a matrix effect. Then when we continued on to some actual food matrices, in this case, a glazed donut or a pastry and a breakfast cereal, again, reporting the numbers that we could see, we do have recoveries that all match between the 80 and 120% criteria for the elements that could be measured. So then we wanted to look at the series of standard reference materials to see what recoveries we could get and how close we were measuring versus certified and reference values. In this case, the standards were diluted at a minimum of 50 times after digestion. Elements with reference values below the detection limits that we could achieve, even with the combination of the USN and the ICP, were not reported. And again, per US FDA EAM, the elemental analysis manual reference value should have a percent recovery between 80 and 120%. So the first one we looked at was the bovine liver. And as you see, comparing the reference values, milligrams per kilogram per dry material to the actual result obtained, we're getting very good recoveries. One element in particular, you'll see that was quite low, and that's cadmium in the liver. We looked at it a little bit more closely, and we wanted to take a look at the emission spectra using the standard nebulizer and the ultrasonic. Now, cadmium is relatively easy to detect, and the 214 nanometer line is a quite sensitive line for cadmium. But with the standard nebulizer, before taking into account dilution factors, we could not see that level of 8.8 ppb cadmium. But with the ultrasonic nebulizer, we could see a distinct peak. Then in the rice flour, again, were for the elements that we could detect at the levels that we could detect, we're getting very good recoveries within the 80 to 120% range. And then finally, also in the non-fat milk powder. So, conclusions and benefits. So, coupling the ultrasonic nebulizer, the U5000 AT+, enhances signal, and it lowers detection limits for important elements, particularly arsenic, cadmium, lead, and selenium. When we did also look at the NIST reference materials, we can also achieve accurate nutrient results necessary for package labeling. The setup is fast and easy with the host ICP-OES, at most about 15 minutes, even after turning on and warming it up, and then you can start pumping samples in. No computer control is required, so there's no software to load onto the host ICP computer. Once it's hooked up and everything is at temperature, you can start pumping samples. And as I showed you in the picture, it's one button operation. You simply press the yellow button on the front of the unit and the aerosol starts, and you can continue to pump samples. You don't have to do anything else to the ultrasonic nebulizer. And I did allude to some details in the name, U5000 AT+. U, of course, alludes to ultrasonic nebulization, and 5000 is a model number. But the AT part refers to auto-tuning, and that's in part of the ease of use with the one-button operation. Once you press on that one button, the system will auto-tune to the different level of sample matrix that comes across the quartz faceplate. The small plus sign is an allusion to Peltier cooling or electrothermal cooling. There's an electrothermal cooler built in the unit, so you do not have to have any type of a recirculating chiller device to cool down the condenser of the ultrasonic nebulizer. That keeps the unit compact and easy to set up. So there are two main part numbers for ordering. There's a 115 volt version of the ultrasonic nebulizer, and there its part number is given, and a 220 volt version. So either of those two, depending upon the voltage requirements in your country, can be acquired. And then, depending upon the model ICP you have, interface kits are available for all contemporary and quite a few legacy model ICP emission systems: Agilent, Analytic Jena, Perkin-Elmer, Shimadzu, Spectro, Teledyne Lehman, Thermo Fisher. One interface kit is provided at no charge with each order of a U5000 AT+. Additional kits can be ordered if you want to put it on an additional ICP, perhaps, if you have another model in your laboratory, but the cost is very nominal. It's simply a kit with tubing and any connection pieces that are needed to interface with the model ICP that you have. So an acknowledgement, special thanks to Mary Jo Menke-Wright for her work on the sample preparation, method development, data collection, and outline text for this important application. As you can see, she did a lot of work and made sure that she looked at quite a good variety of different food sample types, both beverages and food, and then appropriate NIST food matrices to ensure that we had good recoveries of both major and minor elements. So, where to go for more information? Of course, if you do have an existing ultrasonic nebulizer, you can contact our service team if there are any service issues with the unit. Sales support if you're interested in ordering a unit or any supplies for your ultrasonic nebulizer. Technical support, certainly myself at fred.smith@teledyne.com, or my colleague Paula Duscott at paula.duscott@teledyne.com. And I've listed some links below for some web information about the ultrasonic nebulizer and directly into this application. There are additional application notes, of course, located on our website, and you can access those at your convenience. So as Shelley mentioned, if you have any questions, please send those through the email, and they'll be forwarded on to myself, and I will answer those as soon as possible. And thank you, everyone, for attending the webinar today. Again, this is a very timely topic. Detection of trace elements in food matrices has gotten a lot of attention lately. And thank you also, Shelley, for your work, logistics, and setting up the webinar. And with that, we'll end the webinar for today. And again, if you have any questions, please email those in. So long.